This is the 27th and the final lecture of Engineering Physics 1. In this lecture, we will dive a little bit more into thermodynamics, and we will look at the concept of entropy. The entropy is one of the most fundamental concepts, not only in thermodynamics, but in the whole of physics. And it's a pity that we only have one day to go through it. The chapter on entropy in your textbook is kind of a bit complicated. It's definitely too much to learn in half a week. So what I did was I tried to simplify the entropy discussion by getting rid of lots of things like references to ideal gases. So what I have on my slides and in this video lecture is basically a condensed version that you will need to be familiar with to tackle the homework exercises. Let's start this discussion by thinking about heat exchange. So we've said this many times that if you have a hot object, let's say this is hot, and you have a cold object, if they are not insulated, if there is a contact between them of some sort, then there will be a flow of thermal energy from hot to cold. And this flow of thermal energy will continue until both of these objects reach the same temperature, equilibrium temperature. This is how it happens in life. We rarely question why this happens. But if you think about this from a fundamental point of view, there is really no reason why heat should only be flowing from hot to cold and not from cold to hot. So you can imagine a scenario where you have something that's hot, something that's cold. The heat flows from cold to hot. Hot becomes hotter, cold becomes colder. This could happen in such a way that the energy is still conserved. Cold could lose 50 joules of energy. Hot could gain 50 joules of energy. The conservation of energy would still be respected. And it's not clear what is it that prevents this kind of process. There isn't really a law that we studied in mechanics that will say, oh, this is not allowed. So let's think about this from a microscopic point of view. If we take a microscopic point of view, then hot objects are made of hot molecules. They move very fast. And cold objects are made of cold molecules that don't move as fast. And the transfer of thermal energy happens because when the hot molecules and cold molecules interact, the energy of this molecule goes down and the energy of this molecule goes up. Hence the transfer of energy. But if you think about this, let's think about, let's say these are molecules made of one atom. So they are kind of like billiard balls. And if you have two billiard balls that collide, so let's say this is before, and then this is after. Then this collision, we talked a little bit about collisions, although we didn't do them in 2D. This collision can be solved by applying conservation of energy and conservation of momentum. So energy before and after and momentum before and after have to be conserved. But the thing about collisions is that if there is a collision, so let's say this thing is moving faster, this thing is moving slower, and then they exchange energies, you could always run any collision backwards in reverse. So instead of time going in this direction, you could make time move in this direction. And in this case, you have two molecules that are moving back, are colliding, and are then scattering like this. And for every collision, you could look at an inverse collision, and the inverse collision is also possible. In fact, if I showed you a video of two billiard balls colliding, and if I didn't show you the players and the cue, then you wouldn't be able to tell whether this process went backwards, or whether it went forwards, because both of those things could in principle happen. So it's not the case that when a hot, quote-unquote, molecule collides with a cold molecule, that necessarily the energy of this should go up and the energy of this should go down. There are some collisions where this happens, and there are some other collisions. It depends on the angles and things like that. But there are some collisions where the opposite could happen, where the cold molecule exchanged energy in such a way that it became even colder, and the hot molecule exchanged energy in a way that it became even hotter. And it turns out that the reason in real life heat always flows this way and never flows that way has to do with the probabilities. So in principle, there is no law of physics that prevents this from happening. It's very, very unlikely in real life, given usual circumstances, for this to spontaneously happen. So I will now talk a little bit about the probabilities and what this means, that the heat flow from cold to hot is less probable. And to do this, let's think about a simpler example. Let's think about a box, and let's say we have two objects in this box that are randomly moving around. Okay, they're randomly moving around at any instance of time. They could be, if I divide my box in two partitions, at any instance of time, they could be either in the left partition or in the right partition. Now, let's think about how many possibilities are there. If you think about this, there are four possibilities. One possibility is that particle number one is in the left partition and particle number two is in the right partition. The second possibility is that particle number one is in the right partition and particle number two is in the left partition. Then there is a possibility that both of them are in the left partition, and then there is a possibility that both of them are in the right partition. So there are four possibilities. Each one of them is equally likely. And if you look at these possibilities, you will see that half of the time you will see the particles evenly divided between the number of particles evenly divided between the partitions, and the other half of the time you will see both particles being in one of the partitions. Now let's do this with three particles. If you do it with three particles, then so they're randomly moving around. In how many ways could they redistribute themselves between left and right partitions? I will just draw all the possibilities. So one possibility is that they are all in the left. Another possibility is that they are all in the right. And then we have three different ways of arranging them, where two of them are to the left and one of them is to the right. So I say three different ways because if this is particle number one, this is particle number two, this is particle number three, I could have 1, 2, 3 3, 1, 2, and 1, 3, 2. There are also 3 ways of arranging them so that 2 of them are on the right and 1 of them is on the left. And I think this kind of exhausts all the possibilities. I don't think there are any more possibilities. So now, when you look at this distribution, you will see that it's only in 2 out of the 8 cases that you see all of the particles being in the same half. And in 6 out of the 8 cases, they are kind of evenly distributed, 2 of them in one half, 1 of them in the other half. We could continue doing this. On my slide number 3, I have a drawing with 6 particles. So these 6 particles are moving around. If I take a random snapshot, in how many ways could I see them distribute over left and right partitions? And if you, this will probably take some time, but if you, again, if you list all the possibilities, there will be one possibility, one case where all 6 of them are to the left. There will be one case when all 6 of them are to the right. And then there will be 6 cases where you have 5 in one partition, 5 to the left and 1 to the right. There will also be 6 possible arrangements where 5 of them are to the left and 1 of them is to the right. And then you will have other arrangements. And there will be lots of arrangements where 3 of them are to the left and 3 of them are to the right. So let's see how many are there. If I have a 3 by 3 split, then I could have particle 1, 2, and 3 here, 4, 5, and 6 here, 1, 2, and 4 here, 3, 5, and 6 here, 1, 2, and 5 here, 3, 4, and 6 here, 1, 2, and 6 here, 3, 4, and 5 here. And so you get the idea. There are lots and lots of possible ways for them to arrange themselves so that the number of particles splits evenly, 3 on 3 between both halves. And there are only 2 possibilities for them to be all on one side and all on the left side or all on the right side. There is a proper way of doing this. It's called combinatorics. This is a branch of mathematics that teaches you how to properly and systematically and in a principled way compute these probabilities and count the number of permutations. We're not going to be using a lot of combinatorics. The most important thing is that you get the idea, and the idea is that when you have lots of particles, there are more ways for them to distribute them evenly between 2 partitions, and there is only 2 ways for all of them to be either in one half or in the other half. The math that's involved is kind of complicated here, but the basic idea is that more particles you have, if instead of 6 we have 100, the less likely it becomes that they will be not uniformly distributed, and the more likely it becomes that they will be uniformly distributed. Now, when thinking about atoms and molecules, it's important to keep their sizes and numbers in mind. So a typical room, 10 by 10 by 8 feet, will have of order of 10 to the 26 air molecules. Now, this is a huge number. And if we do the combinatorics computations properly, then the probability that all of those molecules will end up randomly in one half of the room will be so small that even if you drew like one random distribution every second, it would take you much longer than the age of the universe to ever randomly come up with a distribution like this. So with large numbers, not only is it very unlikely that all of the molecules will be in one half of the room, it's also extremely unlikely that the balance in the distribution of numbers will be offset by even as small a number as fraction as 1%. So again, I'm not explaining this properly because there is a lot of math involved here that I just don't have time to go through. But the basic idea is that when you have large numbers, when you throw them randomly around, distribution almost always looks uniform, and it's very unlikely that the distribution will be non-uniform, significantly non-uniform. Well, what does all of this have to do with the flow of heat? Well, it turns out that exactly the same principles apply to the distribution of heat. Thermal energy, when you have collision and interaction of hot and cold molecules, in principle, anything could happen. We could end up with an exchange of energy that goes this way. But when you compute probabilities, when you look at all the possible cases, it's overwhelmingly unlikely that the heat will flow from cold to hot. And it's overwhelmingly involving the number of, keeping in mind the number of molecules that are involved in thermal processes, it's overwhelmingly likely that the energy exchange will happen to be from cold to hot. So now what we will try to do is we will try to put some numeric value on this. We will try to make these arguments more quantitative. So I want you to think about two objects again, a hot object and a cold object. So let's say this is hot, this is cold, and the heat flows from here to here, of course. Now, if I look at the amount of energy that the hot object gave away, it will be equal to the amount of energy that the cold object received. The change in thermal energy of hot will be negative. This will be a negative number because hot object loses thermal energy, and the change in the thermal energy of the cold object will be positive, and these two numbers will be equal. Now, since hot object has higher temperature and cold object has lower temperature, if I construct a number which is delta QH divided by TH, so I divide the amount of heat by temperature, and let me call this the change in entropy. Then let me call this the change in entropy of the cold object, and this is the change of entropy of the hot object. Then since the Q's are equal, and this TH is higher than TC, this number will be less than that number. So delta SH will be a negative number, and it will be less than this delta SC, which is a positive number. So if I take the sum of delta SH and delta SC, I will get a positive number. This will be more than 0. So what I did here is I made this construction. I called this entropy, and I denoted it by uppercase letter S. And then I said that every time the heat is exchanged, hot object loses entropy, cold object gains entropy, but the net result for the system is that the entropy goes up. The net entropy goes up. Now this is probably very confusing. The entropy is always very confusing, especially if you when you aim to cover it in 15 to 20 minutes. So the good thing is that we're not gonna go into very much depth. This kind of looks like an overly complicated way of saying heat flows from hot to cold. So I defined something very ad hoc, and then I said this something has to increase, and that's why heat flows from hot to cold. This feels very unnecessary and unnecessarily complicated. But the thing is that later, when you learn, if you learn thermodynamics, it will turn out that entropy is actually a very fundamental quantity. So instead of being this auxiliary variable that helps us define direction of the heat of direction of the flow of thermal energy, it starts to acquire a life of its own. And the fact that the entropy is increasing turns out to be one of the fundamental laws of physics. So basically, just to repeat, I defined the change of entropy as the amount of heat divided by temperature. And then I said that every time thermal energy is exchanged between objects, the net entropy will always go up. The change in net entropy will always be positive. You can read your textbook or other kind of online material on this. The mathematical picture is kind of complicated, but the qualitative picture is pretty interesting. So if you think about this, when you have hot and cold separated, you have some sort of structure. And when hot and cold reach a common temperature, you have kind of this uniform bland distribution of energy. And the increase of entropy in this case means that if things are left to their own devices, they tend to move towards the state of maximal disorder. So if there is some sort of structure, hot, cold, this structure will be erased, and the opposite will never happen. This structureless, uniform distribution of thermal energy will never separate itself into hot and cold, because that would imply that the energy, that the entropy is going down, and we know that just doesn't happen spontaneously. Okay, so all of this is kind of a bit theoretical and confusing probably, but what I will do in the second half of the lecture is I will go and look at some specific examples, very simple examples of two objects exchanging heat, and we will see for those specific examples how to compute entropy, and that computation will come out to be not as complicated.